You see, I haven't watched it, but what I can assume is that since one is taking majority of nations from Spain as refugees to provide us social services, actually education opportunities in school, paying to it is a lot of costs. And people that were trying to get and basically the opposed to conservatives have developed this this perspective that we couldn't give preferential treatment and the opposed those type of opposed they don't like them. They don't like it, and they just say, okay, you can see this is the first time.
Okay, pendulum experiment day. So if we're going to look at a pendulum and like watch what happens, what's something that we could measure, one that we can predict, and then second that we can measure so that we can directly compare. Like here, I predicted that this would happen, I measured this would happen, I was off by 5% or 1%. So what do you think? For if you're watching a pendulum, what's something that you could measure from its motion? Yeah. We could look at max angle. Is that something that like our differential equation would tell us?
There is like just a regular data term in there, so could that be calculated?
Yeah. Yeah, so here we know that the acceleration is always some function of the angle. That the bigger the angle, the more acceleration we have. So if we had like an accelerometer, then we could measure like what is the acceleration as its angle changes or something. I don't have the accelerometer today, sorry. I mean, technically we all do if we like mount somebody's phone onto it, but there's more data processing there. Okay, anything, what else could we measure for this one? What can we predict and then measure?
Time period.
A time period? How do we predict a time period?
Like solve for when acceleration is 0, and then every time acceleration is 0, time between would be one time period.
Okay. So let's say we have, we'll do down to the foot, and then we're going to have one Professor Cooper length pendulum. So 5'9". What is the time period for a pendulum that is 5'9"? Any idea how we can get there? Yeah. Yeah, there's that root G over L, right? What is root G over, what, like, I know we can calculate it, but what is that? Omega, okay. What is omega? Yeah, a lot of times it's omega, right? Yeah. What was omega?
Angular acceleration.
Angular it's, yeah. Sorry? It has to do with like that radians per second, right? Because it is, the measure is radians per second when we take, because we end up with a length per length and then a length per second squared. But it's kind of a weird radian per second thing. Oh. So we'll end up with something as like radians per second. Is that telling us like how fast the pendulum's moving? So for a given pendulum, it always moves at the same angular velocity? I mean, we can watch it. If you watch it, like, it's not always, we'll go big. At some point it goes to 0 speed, right? Because it stops and goes the other way. So omega is not telling us how fast the thing's going. What is it telling us? This one's weird because we're measuring angles in radians, but this is like, yeah.
Aren't you measuring like the angular displacement?
Well, if we're looking at angular displacement, if you're saying I'm moving at so many radians per second, measuring an angle, then you're still saying like the speed is a given value, yeah. But this is not theta. This is not telling us theta. This is what I was. It's a different measure. So really what this is saying is that after 6.28 radians, so like one full cycle, 2 pi radians, then I'll have gone from my start position through a full cycle and I'll be back to where I started. That's what this radian is measuring, of like what fraction of my cycle have I gotten through. So it's radians of a cycle, not of actual motion. So this is called the natural frequency. Natural frequency. So if I know, so what is that? What's 32? What's square root 32 over 5.75? I don't know it offhand. I'm not good with square roots of decimals. .36. How do I get 2.36 radians per second into like time, into like a time period? How long is it going to take to do one full cycle? Yeah, like somehow we got to get rid of that, like we got to use the fact that there's 2 pi radians per cycle. So we're doing some unit analysis. So there's like that factor of 2 pi. Divide by 2 pi or multiply by 2 pi? Divide by? Okay. So if I want to get to usually omega is like radian per second. F, like frequency, is now cycles per second. And that's that omega over 2 pi. Because this is a radian per second. This is a radian per cycle. So what's our frequency for a 5'9" pendulum? .36 over 2, so 1.18 divided by pi. Small. .375. Okay. Or sorry, seconds. Yeah, cycles per second. So every third of a second ish, something like that, we'll have 1 cycle. How are we doing? Does that look right?
Explain again what the cycle is.
So so if we're watching, like, this is 1 as I go start back to where I began. So there's 1, 2, 3. Yeah, that's important to recognize, like, what is a cycle? Because next step is like, how many cycles in how many seconds did we actually measure? So what's the time period? How do we get to a time period? 1 over? 1 over? 1 over f. All right, nice. And if we want, we can do it all fancy, right? We can say that it's 2 pi over omega, which is 2 pi over root g over L. So how long does it take for 1 period to happen for the pendulum? Got it? 2.6. How does that look? Seem reasonable? Which equation did we use, number 1 or number 2, to make this prediction? We didn't use either of them, right? But implicitly, when we said the natural frequency is root g over L, we chose one of these. Do you know which one we chose? We made assumed that one of these was correct. Number 1.
That it's a small angle, then sines and small angles correlate on them.
Yeah, yeah. So number 2, right? Because we assumed sine was a small angle.
Theta was a small angle. And acceleration PC was, I don't know.
Oh, talked out of it. Yeah.
Well, if we assume that small angle,
Okay. Yeah. Is the natural frequency, did we assume that it's a small angle because of the natural frequency? What did we see the difference was? So last time we were like plugging in different angles and looking at like comparison of the time period between a small angle and a large angle. What was different between, did large angle always have the same time period? Or did that one change? I know, this is like 2 days ago. What are you talking about, man? So long ago?
Isn't it the length of the pendulum that
The length changes it.
I remember the period did stretch out. Like, the 1 week.
Two time periods. Yeah, so 60 degrees. So 60 degrees, we have like a stretched out time period. So kind of large-ish angles, it changes that natural frequency. Natural frequency is like time period, like somehow 1 over that time period. So when you say that the natural frequency is constant, that it's not going to change, then really what you're doing is saying that I'm assuming that this is a linear differential equation, so natural frequency is a constant number. That's fine. It's fine to do that, but when you do that, just know that that is an assumption. So swinging on a swing set up to like 90 degrees, you're not going to have a constant natural frequency, like it's a function of how big that angle is. That's okay. Okay, so now we have time measured, and then make this one bigger, right? See if we can still see it. Oh. Did I close it? I did. We'll get it back. All right. That way we can measure it. Do we see our prediction? Yeah, 2.66 seconds. So how are we going to try to measure how long this thing, like how many cycles do we want to use to measure the time period? 10? 10 sounds good.
What's your starting angle?
Does that matter? That's a good question. Is this going to be a function of the angle? Like if we use a bigger, I mean, if we're using 90 degrees, things are a little different. But if we're using like 15 versus 13 degrees, is that okay? It's okay. Should be the same, right? Because a bigger starting angle means it's going to move quicker, but it's going to swing through back up to the other side. So we'll still do the same. That's why if you ever have the option, like, hey, we can either like manually measure displacements or angles or something, or measure time periods and frequency. Frequency is so much easier to do because you just need a stopwatch and a signal. So here we'll use like our eyes, and most other things you would use like Fourier transforms or something. But, all right, so I'll get it swinging. Do we have timers? We got 1, 2, any more timers? Usually, even if we're not good at timing, if we get enough, then the average result will be pretty good. And we'll count out 10 cycles. Sound good? So I'll get it swinging, and then as it gets to the far side, I'll say start, and then we'll all count. And we'll go through 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. How did it go? 10 is nice because we just have to move a decimal over by one spot. So what did we get? What were the measurements? 2.7? 7
That's what I calculated. It was.
Oh.
I got 27.15.
27.15? What else did we get? 27.1. Whoa, pretty.
26.98.
26.98. Man. 27.11.
27.01.
27.01. You good? Is that enough data? That's pretty good measuring. At least like very consistent. Yeah.
I didn't get it down. I was wondering, you had used the length as 5.75 feet for our calculation, right?
Yeah.
But the length of the pendulum that you had used was like longer than 5.75 feet.
Was it?
Or was it like measured out? Because it looked like it was like way longer. I don't know, I could be wrong.
I used my height as the 5'9" measurement.
Oh, okay. Then never mind. I just thought like the height was bigger.
Yeah, no. And yeah, maybe it was, I don't know. It looked like 6. Yeah, it was yeah.
It was like.
And it was a little bit off the ground, I think. Yeah. I don't know how tall is this thing. Is it about 6 feet? Maybe. Like 6 foot.
From here, just everything looks so tall.
Yeah. It's part of the Yukon establishment of power. All right, so what do we got? Do some averaging here. It's all about 27, right? Yeah, 2.71 seconds for, if we take all those values, average, divide by 10 to get over 10 cycles and 5 different timers, 2.7 second. And what did we get? 2.66. What's the error? How wrong was our prediction? How wrong were we? 1.9%? Okay. 1.9? Like 0.05, right? 0.05 seconds? Yeah. So we're off by 0.05 of a second. Is that good enough? Pretty good, pretty darn good. Where's the error coming from?
This, maybe from not enough trials or human error.
Okay, so you think there's like measurement error? So measurement error is definitely, like, it's always going to be there. We can only measure things so well. I mean, if we look at how off our individual timers were, we were all within 0.2, less than 0.2 seconds over 27 seconds. So that's a 0.7% error. So there could be like 0.7% error in just how we're doing this measurement. And we use 10 periods because, like, even if we had done one period, we probably would have all been off by about 0.05 something like that seconds anyway. So it helps decrease that measurement error. So that one, it's definitely part of it, but we're off by like 2%. I'm not too worried about 2%, but it's 2%. It's not like 0.0 something percent or point something. So what do we think? What else could it be?
Like when we use the equations, we do an ideal scenario.
Okay.
There's no drag.
There's no drag. Yep. So is it possible that our free body diagram and our equation of motion is not, like, we're missing something? Do you think that that's the case? That drag is bigger than we thought, or the Yotvos effect, like the fact that when it's moving west, gravity is different than when it's moving right, moving east? That one's like negligibly small. It's Coriolis effect, maybe. We assume the planet was stationary, but it's actually rotating. None of that. No?
When you were just holding it in your hand, it wasn't like a fixed point, so your hand could move a little bit.
Okay.
Kind of help it either side.
Did it look like? Yeah, but I mean, yeah, it wasn't like super steady. But do you think it's like 2%? Like it should have been fixed, but it was actually moving by 2%?
I don't think that's all of it.
Maybe not. Yeah. Add them all. You think it's compounding? So the 0.01% from a. I think we're still on the air, like fractions of a percent though. But fractions add up. Like at least if they actually compound, and they happen to all add error. Because some of the errors will cancel out, like the fact that my hand moved might cancel out the fact that there was drag. One created an increase and the other created a decrease. But actually natural frequency, even for a pendulum sliding, like if it was on a track and bouncing, the natural frequency, at least one of the natural frequencies is still like that root G over L. And it depends on how, like if you have a controller on there. What about length of the pendulum? So at least when I look at this equation, there's only one variable that I had to measure. Like G, I'm assuming that we've measured pretty accurately over time, and usually that's a good assumption to make. But L is something that I measured like on the spot. How accurate, and it was the first thing that was brought up, was like, how accurate is this L? Like it looks like 6 feet, and you said 5.75. How accurate is L? Not so accurate? Ballpark. plus minus a foot, few inches, okay? So here, and you can do like a stats analysis of like what is the partial derivative of this, and like multiply by the error that you expect in it. But a quick engineering approach is like we have this equation, right? Oh, I want this guy back. Oh my God. You want to say 2 inches or more? 3 inches? Or is 2 inches? But like, what is the range of time periods that you would calculate if you were 2 inches longer than what you thought, or 2 inches shorter than what you thought? What are those two numbers? Because we predicted 2.66, but now we're going to get two different values. One bigger, one smaller. Yeah, I have it kind of plugged in up here. 2.69, 2.62. We're still, yeah, we still measured like a little bit above, but 2.69 versus 2.71. Now we're even smaller. Now we're down to like those measurement errors that we were just talking about. Like, how consistently can we hit start and stop on timers? So we're getting pretty darn close. At least that's the way I like to do a quick gut check of like, how accurate am I measuring this stuff, and what range do I actually expect on these things? Cool. So it seems to work, right? Like even with no analysis of like how much error there could be, we can predict the motion of the pendulum and get the time period within 2% by saying there's just tension and gravity. No drag, no friction, no other effects on this thing. Cool. All right, bigger is better, right? So now we'll make like a 3-story pendulum, try to measure time period for that one. So we can use same process, and I'll stick it out my office window, and we can see it from the back of E2. That'll be that's our next step, and then we'll call it a day. Sound good? All right, so if you're watching online, we're leaving. Bye. It's harder to record that.